So we have a great pleasure to have the first lecture by Ashoke Sen. He will tell us about black hole index from gravitational path integral. Please.
Thank you. Okay, so this is the title of my talk, and I apologize that this perhaps is not quite the topic of the conference. But nevertheless, since the organizers asked me to give a talk, I'll give a talk, and I thank you for it. So what I'll be describing is an overview of the subject, computation of black hole index from gravitational path integral. And this will be based on the work done with various collaborators, Anupam, Mathira, Chandramouli, Shanmugapriya, and Amitav. And I'll be describing some of this work, and I'll also refer to the other people's work when time comes, when I make use of it. Okay, so let me begin with some brief history of the subject. Now, this formula you have seen many times by now, the Bekenstein-Hawking formula, and I'll be using the natural units where I'll set h bar c, g Newton, and the Boltzmann constant to 1. Now, when you apply it to specific theory, okay, like say Einstein-Maxwell theory or extended supergravity in d dimensions, the black hole can carry U1 charges, which I'll denote by qk. In general, there may be several U1 charges. It has angular momentum, okay, gi in the Cartan subalgebra of SOD minus 1, and it carries some mass, and we can express the entropy as a function of the charges, mass, and the angular momentum. And q and j can have multiple components. Now, if you work with a two derivative action, like the Einstein action, or even extended supergravity, then it scales as lambda to the d minus 2 if we scale the various fields according to the tensorial rank. So if we scale the g mu nu, the two-form field, the gauge field, and the scalar in this way, one can easily check that the action scales as lambda to the d minus 2, and this translates to a scaling property of the entropy. So if you scale the various charges, then the entropy scales again as lambda to the d minus 2. And this makes it easy to take the macroscopic limit or the large size limit, because you simply scale the mass, charge, and angular momentum in this fashion and take lambda to be large, and in that limit the black hole is large and the Bekenstein-Hawking entropy is also large, scaling as lambda to the d minus 2. And a general theme that we'll have to keep in mind is that our goal will be to compare the entropy with log of degeneracy from some microscopic counting of degeneracy of states. Now, it will also be important for us to introduce the chemical potentials. Okay, so we define the inverse temperature beta, the chemical potential corresponding to the charges, and the chemical potential for the angular momentum, which is also known as the angular velocity, in this fashion. And we should keep in mind that because q and j have multiple components, in general mu and omega also have multiple components. And using these scaling relations, okay, one can also figure out how the beta, mu, and omega will scale. The reason that these are important is because in the gravitational path integral, these set the asymptotic boundary condition and are taken as independent variables. Okay, so instead of thinking of the charges and angular momentum and the mass as the independent variable, it's more natural to think of these as independent variables, and from this you compute the mass, charge, and angular momentum. Now, the Bekenstein-Hawking formula is expected to receive corrections. These corrections can be due to stringy effects, okay, which typically take the form of higher derivative terms in the action, but also quantum effects. Now, if you are restricting our analysis to the classical theory with higher derivative terms, okay, this is what I mean by stringy effects, then these corrections are given by World's formula, who wrote down a general formula that expresses the entropy of a black hole in the presence of higher derivative terms in the action. But in the full quantum theory, we need to rely on gravitational or string theory path integral. Okay, and we will come back to this later. This, of course, follows the work of Gibbons and Hawking many years ago. So the general structure of the entropy that we expect is that there will be a leading term that scales as lambda to the d minus 2, as we saw, and then there will be power suppressed terms, but there can also be logarithmic corrections. Okay, these logarithmic corrections typically will come from quantum effects. So the strategy that one uses for comparing the black hole entropy, or what I'll also call the macroscopic entropy, with the microscopic results is the following. So we first construct a configuration of branes and strings in string theory that carry the same mass and charge as the black hole. Then we compute the entropy by counting the number of states of this system, and finally we compare this with the results given by the Becker-Hawking formula. This is the general scheme that we would like to implement. But this scheme runs into the following problem. The computation of degeneracy can be done at weak coupling, weak string coupling, where the dynamics of the branes is best understood. Right? So that's the first step. On the other hand, the black hole description of the system is valid only when the gravitational coupling is strong enough so that the horizon size is large. Okay, otherwise it doesn't make sense to talk about these as black holes. So they are valid in two different regions in the coupling constant space, and then the question arises, how can we compare the two expressions? And this is a question that we will try to address. So the answer that we normally follow, at least for precision comparison of this kind, is that we compare supersymmetric index of BPS black hole, and the reason for comparing, focusing on supersymmetric index is that it does not change as we vary the coupling constant. There are general results that if we take supersymmetric index of BPS, for us will be synonymous to supersymmetric black holes which preserve certain amount of supersymmetry. So there are general arguments that supersymmetric index does not vary as we change the coupling constant. And indeed, many BPS indices have been computed in string theory using microscopic description. So once you have a brane system, you can compute the index, and then you are guaranteed that the index will not change as you change the coupling constant. But what about on the black hole side? Now, the usual argument that one gives on the black hole side is that generically all states that are not protected by index will become non-supersymmetric and acquire additional mass. And hence, for black holes, index and degeneracy should be the same. And then, of course, degeneracy is computed by exponential of the entropy. So this is the way one compares an index computed on the microscopic side with entropy computed on the macroscopic side. Now, I should add that there are also other arguments for why index and degeneracy should be equal, but none are really foolproof. Okay, so this is a question that remains open about whether it's fair to compare index with degeneracy. Nevertheless, people did go ahead and make this comparison. So we compared the microscopic results for log of index and the macroscopic results for entropy, and one finds that it agrees very well. Okay, this has been done for a wide class of supersymmetric black holes, and it agrees very well. And indeed, to the relevant order, first of all, one has perfect agreement with the Becker-Hawking formula when the black hole size is large. But then one can go beyond this. One also finds perfect agreement with higher derivative corrections computed via World's formula. So on the black hole side, you use World's formula. On the microscopic side, you do a finer counting. And again, the results agree. And finally, there is also perfect agreement for logarithmic corrections to the black hole entropy. And this is, of course, computed using gravitational path integral. On the microscopic side, the answer is the same, right? That is the overall answer, and you have to just study it in appropriate approximation to pick up the logarithmic corrections. And again, one finds perfect agreement. But then one can be more ambitious and ask, is it possible to calculate the index directly on the black hole side? Right? Because this at least will remove the doubt about whether you are comparing apples and oranges, right? We will be computing the index on both sides. And recently, a method for doing this has been suggested. Okay, this was suggested in this paper. Okay, they formulated it in flat space time, and that's why we are going to use this. And earlier there is a paper that formulated in the context of ADS black holes, but we will be using mostly the formalism developed here. And our goal will be to use this method, which I'll illustrate, which I'll explain later. We want to use this method to test this index equal to degeneracy postulate, and then we can compare the index of macroscopic and microscopic computation. So let me now give a general overview of supersymmetric index. So let's suppose that you have a black hole in d space-time dimension, and we now identify some Cartan generator of SO d minus 1, one particular Cartan generator, okay, and call that J0, and J prime will be a collection of the other Cartan generators. At present, this choice is up to you, how you choose J0 and how you choose J prime. Given this, we can define a supersymmetric index as given here. So this trace is taken at fixed charge, fixed values of all the J primes, zero momentum, and what you put inside the trace is e to the minus beta h, where beta is the inverse temperature, 2 pi I J0. So for now, beta is just a parameter, e to the 2 pi I J0, that object over here, and 2 J0 to the n. And then the trace is taken over states at fixed values of these, right? That's important. Now, why is this important? One can generally argue that the index is expected to pick up the degeneracy of the states that break 2n or less J prime invariant supersymmetries. So just to give an example, imagine that you have n equal to 2 supergravity in 4 dimensions. N equal to 2 supergravity has 8 supercharges. So the number of supersymmetries is 8. And suppose you want to count the half BPS states. Right? The half BPS states preserve 4 supersymmetries, so they break 4 supersymmetries. Okay. So the number 2n here should be chosen as 4. Right? So correspondingly, you want to calculate this index for n equal to 2. So the idea is that this picks up contribution from BPS states, but not from a generic non-BPS state, because a generic non-BPS state will break more supersymmetries and they don't contribute to the index. Okay. This is, you can recognize that e to the 2 pi I J0 is essentially minus 1 to the f. That's what enters within the index. Okay. The reason that you need this is the following, that imagine that your n had been 0. Okay. If n had been 0, okay, then the index will pick up contribution only from those states which break 0 supersymmetry. Okay. But those are just the vacuums. Right? You are not trying to count the vacuum. So if you are trying to count the vacuum, then we should use Witten index. Okay. Whenever you are trying to count particle-like states, right, it breaks certain supersymmetries, and that's why you have to choose n to be not 1, but an appropriate integer that is controlled by how many supersymmetries are broken by the state that you want to count. So here is this formula again, okay, and I'll define S BPS, okay, which will be a function of q and j prime, because this space is at fixed q and j prime, by this formula. Right? It will be e to the minus beta times m BPS, because m BPS means that this is the energy of the BPS particle that contributes. Okay? Because k is equal to 0, h is the same as m for single particle states, and this is essentially the exponential of the index. So just to give examples, in 4 dimensions, the rotation group is SU2. J0 you can take to be the third generator of the rotation group, and J prime in that case is trivial. Right? There is no J prime. In D equal to 5, the rotation group is SO4, okay, which is here, and we can take J0 to be the third generator of the right SU2, and J prime could be the third generator of the left SU2. Okay? But there are of course other choices in this case. Okay? But if you make this choice, then the index will be a function of J3L and the electric charges. In this case, the electric index will be a function of the electric charges only. So this is the definition of the index, and now we will try to describe how to compute the index using gravitational path integral. So we begin with the Gibbon-Shocking prescription for gravitational path integral. or almost the gibbon sucking prescription. So we perform a path integral over all fields weighted by exponential of the minus action. And the only difference will be that we insert a factor of 2j0 to the n in the path integral, because we want to calculate, we want to insert this inside the trace. And we impose the following asymptotic conditions, that the Euclidean time tau and the azimuthal angles phi are periodically identified in this fashion. Right? So omega, if you recall, is the chemical potential conjugate to the angular momentum. Normally, if omega is 0, that's what we usually deal with, or non-rotating black holes. Then, of course, the identification is just tau is equivalent to tau plus beta. And the time components of the gauge fields are required to take specific asymptotic values that is set by this chemical potential mu. So this is the general setup, but we will set beta omega 0 to be equal to minus 2 pi I. Okay, omega 0 is a particular component of omega that is conjugate to j0. So what this computes, according to Gibbon-Sucking prescription, is something like this. Okay, trace over all states weighted by this factor. Okay, and I have just inserted this 2j0 to the n because we insert it in the path integral. Okay, otherwise, without this 2j0 to the n, it would have been exactly the Gibbon-Sucking prescription. Okay, and because I have set beta omega not equal to minus 2 pi I, you have this factor of 2 pi I j0 inserted inside the trace. So we are going to analyze this formula both from the statistical side and the gravitational side, and then compare. So first, let me describe the statistical side. So here is the formula for Z. Now we use the definition of SBPS that I had already given. This is the trace at fixed q, j prime and momentum equal to 0. This trace is taken over all states. But using this definition, we see that we can rewrite Z as trace over all values of q. So now you sum over all values of q, sum over all values of j prime, and sum over all momentum. And in the approximation that I'll be working, we can just replace the sums by integrals. Okay, so you have the integral over the charges, the j prime and k, weighted by this factor over here. So e to the SBPS minus beta MBPS comes from here. This beta k square over 2 MBPS comes because you have h here, and now for in Z, of course, you are tracing over non-zero k as well. So there is a kinetic term that is kept here, okay. And then these terms are just because you have explicit insertions of these factors over here, minus beta mu dot q and minus beta omega prime j prime. So this k is the momentum that I said, this, but not all momentum are allowed. The momentum has to be invariant under omega prime dot j prime, okay. And this gives you some n-dimensional space of momentum to integrate over. Okay. In 4 dimension, where j prime is trivial, it's the full 3-dimensional momentum. Okay, but in higher dimensions, things can be different. NC prime here is the number of generators, j prime, right? In 4 dimension, again, this integral is trivial. In 5 dimension, it's a 1-dimensional integral, and NV is the number of U1 gauge fields. So here is an expression that written again. Now, the contribution to the integral is dominated by the saddle point where the integrand has a maximum, right? So it's basically usual statistical analysis. We evaluate this by saddle point method. Okay. But in this case, instead of just picking up the saddle point contribution, let's also keep track of the logarithmic terms that we get from the Gaussian integral around the saddle point. So for example, the k integral here, because of this minus beta k e to the minus beta k square over 2 mbps, the k integral will give a factor of m over beta to the nt over 2. And using the scaling of m and beta that I have described earlier, you can see that this will give a factor of log lambda in the exponent of this form. Similarly, the q and j integrals, okay, will pick up similar contribution. You have to take the second derivative of s with respect to q and j. And again, by using the scaling laws that I have given earlier, one can show that this scales as this particular power of lambda. So a net result, okay, up to higher order corrections can be written as S BPS minus beta MBPS, that is the saddle point value. The saddle point value of k is 0, and then again the saddle point values of these quantities over here. Okay, so this is what I have said, that this J prime and Q have to be evaluated at the saddle, and the C, which this subscript E will stand for the logarithmic correction that is coming from the change of ensemble, right? I mean, this is essentially converting from microcanonical to grand canonical ensemble, and that's where these logarithmic corrections are coming from. Yes.
Why did you use the non-relativistic formula for the
Yeah, I could use relativistic formula, but the point is, because I mean, you can estimate what range of k actually contributes to this, and you find that that's a really non-relativistic range that contributes, right? So I could have taken the full relativistic formula, and then you have to evaluate the second derivative at k equal to 0, right? So this is good enough for this. Okay, now on the same partition function can also be computed on the gravitational side. So on the gravitational side, this is again the formula, and the dominant contribution to the gravitational path integral for Z will come from a Euclidean black hole solution with parameters beta, omega and mu. This is what I said, that instead of thinking of M, Q and J as independent parameter, we say that beta, omega and mu we take as fixed parameter, and then M, Q and J would derive from by solving the equations that relate beta, omega, mu and J, omega, m. So this will be then the formula for log Z that you calculate from the gravitational path integral. Okay. So this part is just Gibbon-Hawking result. Okay. S classical is the classical black hole entropy, okay. And in this case I can also include the world's corrections, okay, because we don't need to restrict our analysis to two derivative theories of gravity. So this is a full classical black hole entropy. These are the standard results that come from Gibbon-Hawking analysis. And then again I have added the C log lambda term, and this comes from one loop quantum correction. We'll be describing later how to calculate the C log lambda. And the gravitational path integral also has these two J0 to the n inserted, okay, and that in fact is essential because there are fermion zero modes in this black hole background, and this 2J0 to the n is necessary to saturate those fermion zero mode integrals. Otherwise, you will just get 0. I will come back to this again later. So let's now compare the two results. Okay, so this is the result from gravity, and this is the result from statistical mechanics. So if we compare these two, then you see that we have an expression for SBPS, that is what we want to compute in terms of the classical black hole entropy. This is the world entropy, and all these formula over here. Now you see here that even at the classical level, even if you ignore this one loop log correction, okay, and in fact you can even ignore the world correction, right? You can just think of the S classical as the Bekenstein formula. Okay. Even at that level, there are non-trivial classical identities. Okay. First of all, because we are describing supersymmetric black holes, okay, M classical should be equal to M BPS, okay, and M BPS in turn you can determine it using supersymmetry, but you can also determine it by computing the mass of an extremal BPS black hole. Okay. They are bound to give the same result. Okay. And we also have a relation between S classical plus 2 pi I J0 with S classical BPS. Okay. So if we believe in the degeneracy equal to index formula, right, then this S classical BPS should also be equal to the BPS black hole entropy. Okay. And that you can calculate at 0 temperature non-rotating black hole. Okay. So this side is a result for a non-rotating 0 temperature black hole. This side is a result for a finite temperature. We have not said beta equal to infinity anywhere. This is finite temperature rotating black hole. Nevertheless, these two should be equal. Right? That's what this analysis is saying, because if index and entropy happen to be the same. And this classical relation has been tested in many two derivative theories. These authors, okay, they actually tested it for minimal n equal to supergravity in 4 dimensions. That's basically Reisner-Nordstrom. Sorry, not Reisner, Kerr-Newman. Okay, you need charge and angular momentum. then we tested it in 5 dimensions, okay, where things are a bit more involved because you have also additional angular momentum. And in this paper, they looked at again 4-dimensional n equal to 2 supergravity, but general n equal to 2 supergravity. Okay, and in all of these cases, one does find that these things agree. Okay, but we'll be focusing now on the log correction and see what we get. So C I have already given the formula for, right? Let me remind you again that C came from the change of ensemble. Okay. So let's now briefly describe how to compute the C log lambda term. So by simple power counting, one can convince oneself that such contributions come from one loop contribution of massless fields. Okay, so if you just know the massless spectrum, that's good enough, and you don't need to go beyond one loop. So let's denote by Kb the kinetic operator for massless bosonic fields, and by Kf the kinetic operator for massless fermionic fields. Then we know that the one loop contribution to Z, okay, here we are again doing gravitational path integral. One loop contribution to Z from the massless fields will be given by determinant of Kb to the minus half times determinant Kf to the half. Okay. This is a contribution to Z, so the correction to log Z that you get from this one loop determinant is obtained by taking the log of this, which is here, and then you can also rewrite this as a trace of log of these. Now the lambda dependence, okay, comes in this formula because the bosonic kinetic term goes as lambda to the minus 2, right? A Laplacian has to be contracted with G with upper mu nu, right? And that scales as lambda to the minus 2. And the fermionic kinetic term scales as lambda inverse. So roughly we can think of these, or the lambda dependence of these, as just counting the total number of bosonic modes and total number of fermionic modes. Okay. So the result can be written this way. Oh, I should have said this, that there is standard procedure for computing this, okay, and that's called the heat kernel expansion. Okay, so I'll not describe the method, but I'll just give the form of the result that one gets. So what one finds is that this particular contribution can be written as an integral over the full space-time of some quantity k of x that can be constructed from the curvature tensor and various other invariants of the background. Okay. So the precise coefficients that come inside k requires knowledge of kb and kf, particularly the massless spectrum of bosons and fermions in this theory. Now there is one result which was surprising when it first appeared and its significance was not understood. Okay. But now we see that that's an extremely useful result. Okay. And the result is the following, that if we are considering n equal to 2 or higher supergravity in d equal to 4, okay, then k of x when one computes is proportional to the Gauss-Bonnet term. Okay. The constant of proportionality depends on the particle spectrum, but the actual integrand is proportional to the Gauss-Bonnet term. And that means that a computing CL is very easy because CL is just proportional to the Euler number of the black hole, Euclidean black hole solution. Okay. If this had not been the case, then you have to integrate a complicated object, okay, over the whole black hole spacetime, Euclidean black hole spacetime. And for odd d, CL is just 0. Okay, so this doesn't contribute. So this is part of the log correction from the gravitational path integral. Okay, but there is one more part, and that's the zero mode contribution. The point is that kb or kf may have zero eigenvalues that arise from broken symmetries like the translation, rotation, supersymmetry, etc. Okay. And of course, zero eigenvalues cannot be treated as part of the determinant. Okay, and you have to correct for it. Okay. So there are two steps in this correction. The first step is that we have to remove their contribution from delta log z, because in this formula that I have given here, okay, this just calculates this, okay, without worrying about whether you have zero eigenvalue or not. It just counts 1 for every eigenvalue. So in particular, a bosonic mode gives a contribution of 1 over lambda squared to the minus half which is lambda to z, and hence log lambda to log z. That means that we need to subtract log lambda from delta log z for every boson X0 mode, because you have overcounted. And similarly, you have to add half log lambda to delta log z for every fermion X0 mode, because we had introduced a factor of lambda to the minus half in the determinant. So that's the first step. But then we also need to find the actual lambda dependent contribution to z from the 0 mode integrals. So for this, we have to express the integral over the 0 modes as integral over the broken symmetry parameters and then carry out the integral. Okay, because as I said, 0 modes are associated with broken symmetry parameters. And in this process, there are various sources of lambda dependence that comes in. For example, the original integration measure would have lambda dependence that you have to study carefully. The Jacobian for the change of variables from the 0 modes to the symmetry parameters may have lambda dependence. And finally, the integral over the symmetry transformation parameters can also have lambda dependence. So this translates to some log lambda factor in log z. The analysis is straightforward, but you have to analyze each 0 mode separately and carry out the analysis. Okay. And here let me again mention that the fermionic 0 mode integrals are associated with broken supersymmetry, and they are saturated by the 0 mode part of 2j0 to the n. If this factor had not been there in the path integral, then the result would simply vanish, right? Because the fermion 0 mode integral gives you 0. So I'll just give the final result. So the net logarithmic correction from the 0 modes turned out to be this. So you can recognize that this NT, this is the number of translation modes. So there are translation 0 modes which give this contribution, and then there are also rotational 0 modes which give a contribution of this form. So now we can add up all the corresponding contributions. So remember the net logarithmic correction to SBPS, there is a contribution from C, that is the that came from the statistical side because of a change of ensemble. Then there is a local contribution, that integral over K of x, and then there is a 0 mode contribution that is explicitly given here. Okay. And when you add up, when you use the formula that I had given earlier, this is what you get. Okay. This NC prime, maybe I didn't explain, NC prime is the number of J prime generator. I had said it earlier, okay, but let me remind you that this is the number of J prime generator. So for example, in D equal to 4, NC prime will be 0 because there is only one Cartan generator, that is J0. In D equal to 5, there are 2 Cartan generators, one of which is J0 and the other one is J prime. So here you have then an explicit formula, okay, in terms of some universal quantities like the dimensions and the symmetries, and then the dependence on which theory you are considering comes to this CL. So let me just give the final result. So the final result that one finds is that the logarithmic correction to the index computed from this approach gives the same result as the logarithmic correction to the entropy that was computed earlier. That was quite a different calculation. Okay, background was different. Okay, the ensemble was different. In fact, for the direct computation of the extremal black hole entropy, one uses a microcanonical entropy, and hence we don't get this C factor there. Okay. Nevertheless, at the end, we find the same answer. The index computed from the full geometry correctly reproduces the microscopic results when they are known. So first of all, it agrees with the entropy, and because the previous analysis had shown that the entropy always seems to agree with the microscopic results for the degeneracy or for the index, okay, we also see that the index computed from the macroscopic and the microscopic sides agree. Okay. And this has so far been done in theories with 16 or 32 supersymmetries. That means say n equal to 4 in D equal to 4. Okay. There is a wealth of possibilities for n equal to 2 supersymmetric theories in 4 dimensions, okay, because there are lots of black holes that one knows, but for none of them the microscopic results have been analyzed. Okay, so once the microscopic results are available, the macroscopic results are there. Okay, so once the microscopic results are available, we can go ahead and test whether the agreement continues in that case. Now finally, I should note that so far similar computation for the contribution to the index from higher derivative terms has not been done. Okay? In other words, the classical analysis so far has been only for the Bekenstein-Hawking entropy, but not the world entropy. Okay? Even though for the entropy, we know the answers including higher derivative terms. Okay, so this is an open problem. It seems to be more like a technical problem, okay, but this has not been done. And there is still some work in progress with these collaborators. Finally, let me just say, turn to a slightly different topic. Okay, the same technique, but now we want to analyze a different system, okay, and that's understanding BPA states from elementary strings. Okay, this subject in fact goes back many years. Okay. So we'll consider heterotic string theory compactified on a 10 minus d dimensional torus. And the spectrum of the string contains states that carry electric charges under various U1 gauge fields in the theory. And a subset of these states are invariant under half of the supersymmetries of the theory. Okay. These are the BPA states, are also known as the double Kerr-Harvey states, because they are discovered by double Kerr and Harvey in 1989. The important result for us is that if we go to large charge, okay, then the BPS, the log of the index, grows as square root of q square, okay, where q square is some quadratic combination of the charges. And the question that we would like to ask is it possible to reproduce this result from black hole entropy? This in fact was a question that was asked many years ago, and there are partial answers to this question, okay, spanning 10 years. But this is not exactly the question that we'll try to ask. We are going to change this question a little. And that is, can we compare this with the BPS black hole index carrying the same charge? Okay, not the entropy, but the index. Because now we know how to compute the index. And here one runs into some puzzles. Okay. So recall that we have the scaling property that I described earlier. Okay. Using this scaling property, one finds that this entropy should scale as lambda to the d minus 2. J0 also scales as lambda to the d minus 2. But the microscopic result is given here. And if you look at the scaling property, we see that it goes as lambda to the d minus 3. So there is a contradiction. S0 and J0 are much larger than the microscopic entropy in the large lambda limit. Okay, so this is a contradiction. But when one goes ahead and computes S0 and J0, one finds that neither of them are in fact 0. Both of them scale as lambda to the d minus 2, but the sum is 0. Okay. So at least the immediate contradiction is avoided. But let's proceed to the next step. Okay, so the macroscopic results are given here. This is what I have just described. Now, because G mu nu is of order lambda square, the correction to S0 and J0 from the world entropy will go as lambda to the d minus 4, because the leading terms were lambda to the d minus 2, and every time you go to higher derivative, you add 2 extra derivatives, right, and that gets suppressed by lambda to the 1 over lambda square. Okay. So if the corrections are lambda to the d minus 4, then the sum of the two, because the leading term vanishes, we expect that the sum of the two should go as lambda to the d minus 4. And now we have a contradiction in the opposite direction. Right? The macroscopic entropy seems to be much smaller than the microscopic result that is known. It turns out that there is a resolution to this, and the resolution is that the horizon has singularity on a codimension 2 subspace where the naive scaling argument breaks down. And on this codimension 2 subspace, the string coupling is small, so that we can just focus on the classical contribution. You don't have to worry about the string loop effects. And then there is a defined scaling argument, and this depends on the details of the solution. Okay, we cannot get this result without looking at the details of the solution. But once we examine the details of the solution, one finds that there is a defined scaling argument that tells us that this combination indeed goes as some constant times square root of q square, okay, where k is a universal constant. Okay, it's in fact independent of everything, okay, including the dimension. It doesn't even depend on the dimension. Okay. And that agrees with what we know from the microscopic counting. Okay, this doesn't also depend on the dimension, and it has exactly the same dependence as this one. So this means that there is perfect agreement, okay, Of course, we don't know what k is because we cannot calculate it. And one can show that if we really want to compute k, this requires taking into account all classical higher derivative corrections in string theory. Because once there is a singularity, you cannot just stop at 4 derivative or 6 derivative. You have to really look at the full set of higher derivative terms. If we could do that, then we could in principle compute k, but that has not been achieved so far. So this is where we stand as far as how BPS states are concerned. So let me end with the conclusion. So essentially what I have tried to argue is that we now have a systematic procedure for computing the index of a supersymmetric black hole. It's a little more complicated than computing entropy of supersymmetric black holes because we just use spherical symmetry. Okay. But this is what we can compare with the microscopic results. Okay. So in that sense, this is a very useful tool. Okay. And we have seen that it agrees with the result of microscopic computation in string theory whenever such results are available. And it also agrees with the result for the degeneracy that we compute from the entropy. Okay. So in some sense, we do see that for BPS black holes, index and degeneracies agree to the extent that we have studied. Okay, thank you. I'll stop here.
We're perfect on time, so we have time for questions.
So you mentioned in the beginning that in the past for the non-rotating black hole, the big black holes, the walled entropy corrections have been computed.
Yes.
So the unsolved problem is to compute them for this rotating ones?
Exactly.
The supersymmetric but rotating, I see.
Yeah, exactly.
Ashoke, coming back to why the degeneracy seems to agree with the index. I thought in some cases, but I wasn't able to recall, you yourself had an argument that this should have been the case, right? From the supersymmetry algebra and so on.
That was based on the near horizon geometry, right? But that didn't take into account possible contribution from outside the horizon. Right? There could be excitations outside the horizon. So this index calculation takes into account everything, right? Doesn't matter whether everything is coming from the horizon or there are modes situated outside the horizon and contributing to the index. Okay. That argument was based on the near horizon ADS2 times S2 isometry, right? And that's where we used this argument, right? So, for example, multi-centered black holes or modes outside the horizon, those are not included in this count, in that argument. And it could be that index and degeneracy are not the same once you take into account everything, right? But at least what this is saying is that to the extent that we have calculated, the index and degeneracy turns out to be the same.
And then a quick sort of related maybe, I don't know, question is, so is there a way to separate the gravitational calculation into the ADS region there then and the far region with the ADS region being connected to JT gravity in some way?
Yeah, it's not completely clear that that can be done in this context. If you look at a finite beta, then it doesn't look like there is a separation between the near horizon region and the finite far region. If you take the temperature goes to 0 limit, then I think you can do this. Yeah. But this is really finite temperature calculation, right? Here we are not taking the temperature to 0 anywhere, right? It's a rotating black hole at any temperature that you like, right? Yeah, in the beta going to infinity limit, those, I mean, the earlier analysis that people have tried to do, right? May be possible here also. Because it really, in the beta goes to infinity limit, this configuration really approaches the spherical symmetric black hole configuration. And the rotation goes to 0.
Okay, maybe Shumi?
Yeah, can I ask a question?
Yes.
These are large black holes.
Yes.
But the horizon is still singular?
No. Horizon is not singular, but the singularities are the poles essentially. If you took a 4-dimensional black hole, the singularities are the poles, right? And if it's higher dimensional, basically it's a codimension 2 singularity.
I got it. Yeah. Okay. Yeah.
But that's where the contribution seems to come from. Because from the rest of the horizon, the scaling argument says that the contribution is too small. Okay? So you really need to go to the, towards the singularity here.
Yeah. So here. So these results are valid for the supersymmetric black holes, right?
Yes.
How we can count the microstate of non-supersymmetric black holes?
See, you can count the microstates of the system with the same charge and mass, right? The question is, but the point is that calculation is always done in the weak coupling limit. Right? The question is how to continue these to strong coupling, that we don't know. Right? Typically, if you have non-supersymmetric black hole, then the results will change as you go from weak to strong coupling.
Thank you.
Okay.
So this particular statement about K that you had,
Yes.
the K is not protected by supersymmetry. You said it gets contributions from all higher derivatives.
That's right, yeah.
So, but it says, but you're still computing some supersymmetric states, right? It's a bit.
Yeah, I think as far as I know, there is really no general argument which says that K is protected by supersymmetry. At least no rigorous argument. But it's possible that maybe there is some protection.
But you are counting supersymmetric states, right?
Yes, we are counting supersymmetric states indeed. That is true.
So you might expect, and it's an index, so you might expect that it is protected, no?
Yeah, it's possible. I mean, it's quite possible that maybe we can be done with 4 derivative terms, right? In fact, that right now, I mean, we did look at there's the 4 derivative terms, and somehow we couldn't get a sensible result out of it, right? But that doesn't mean that it doesn't exist. It's that the equations are. I mean, basically, what happens is once you include higher derivative terms, the equations start having unphysical solutions because you get you have more number of derivatives in the equation, right? So you get solutions which are spurious, and it's very hard to separate out those solutions from the physical ones. So that's the technical problem. Hopefully it will be resolved, but that's where things stand now.
Okay, thanks.
Okay, there's no more question. Let's thank Ashoke again.
Thank you.